Hey everyone, and welcome to The Explainer. If you're looking to absolutely master Chapter 5, the periodic classification of elements, well, you're exactly where you need to be. I am so pumped to guide you through this complete revision today.
First off, a massive congratulations to you. You've already put in the heavy lifting and crushed parts 1 through 4. You know the history, the tables, and the trends. So today, for part 5, we're doing a laser-focused, exam-oriented revision to guarantee you secure those full marks. Let's lock in everything you've learned.
Here's our quick roadmap. We're going to hit the initial classification problem, look at the early attempts at order, break down Mendeleev and the Modern Table, decode those periodic trends, and finally tackle the absolute most essential exam questions.
Okay, section 1, the classification problem. Let's get right into it. So why do we even care about organizing these things? Well, imagine trying to memorize the individual quirks, reactions, and properties of over 100 different chemical building blocks. Studying every single one separately without any kind of system, it's just insanely difficult. It's literally like trying to find a specific book in a library where everything is just dumped in a giant, chaotic pile on the floor. And that's exactly why classification is a total game changer. It creates a functional system. Grouping elements gives us the power to study them systematically and easily compare their properties. But honestly, the coolest part? A solid system lets us predict the properties of elements that haven't even been discovered yet. It helps us see the hidden relationships between, well, all the matter in the universe. Moving right along to section 2, early attempts at order. Let's rewind back to 1829. A scientist named Johann Dobereiner made the first real leap here. He started grouping elements with similar properties into sets of 3, calling them triads. But he didn't just guess. He based this entirely on atomic mass. His big rule was that the atomic mass of the middle element was roughly equal to the average atomic masses of the other 2 on the outside. Now, the math here is actually pretty fascinating. Take a super famous triad: lithium, sodium, and potassium. Lithium's atomic mass is 7, potassium's is 39. Add those up, you get 46, divide by 2 for the average, and boom, you get exactly 23. And 23 just so happens to be the exact atomic mass of the middle element, sodium. It's a beautiful mathematical coincidence, but sadly, he could only find a few of these triads, so it wasn't the complete puzzle. Next up, John Newlands gave it a shot with his law of octaves. He lined elements up by an increasing atomic mass and noticed a musical kind of pattern. Every 8th element acted like the first one. But this rigid rule of 8 had some major flaws. It totally broke down after calcium. To force his law to work, he ended up jamming completely different elements together, and worse, his system had literally zero room for any new discoveries. Which brings us to section 3, Mendeleev and the Modern Table. Enter Dmitri Mendeleev. This guy completely revolutionized chemistry with his periodic law. He made atomic mass the absolute gold standard, stating that the properties of elements naturally repeat in a periodic way when you arrange them by increasing atomic mass. The sheer genius of Mendeleev's system was that he actually left blank spaces and correctly predicted elements that nobody had even seen yet. He even left room for noble gases to be added later. But because he relied so heavily on atomic mass, he ran into some unfixable glitches. He couldn't figure out where to put hydrogen, he couldn't deal with isotopes, and he even had a few spots where a heavier element had to go before a lighter one just to make the chemistry work. But then, in 1913, Henry Moseley came along and fixed the whole thing with one incredibly elegant tweak. Listen to the shift here. He swapped atomic mass for atomic number. By organizing elements by their number of protons, every single anomaly Mendeleev struggled with just vanished overnight. All right, section 4, decoding periodic trends. So let's look at the actual structure you see in your textbook today. It is perfectly organized into 7 horizontal periods and 18 vertical groups. The VIPs you absolutely need to remember are Group 1 on the far left. Those are your highly reactive alkali metals. Group 17 has your super reactive nonmetals, the halogens. And all the way on the right, Group 18, you've got your perfectly stable, totally inactive, noble gases. Now take a mental screenshot of this grid. This is your ultimate cheat sheet for periodic trends. Notice the rhythm here. As you move across a period from left to right, atomic size and metallic character both decrease, while non-metallic character goes up. But when you move down a vertical group, the exact opposite happens. Atomic size and metallic character both increase. Valency is its own weird thing. It climbs up to 4, drops back to 0 across a period, but stays exactly the same all the way down any specific group. And finally, section 5, essential exam questions. Time to put all this knowledge to work.
We're starting with the 1-mark quick-fire questions. These are the absolute basics you need to know instantly. Take a quick look. Do you know the answers off the top of your head? If you said properties are functions of atomic numbers, there are 18 groups, and the whole thing was proposed by Henry Moseley, you nailed it. Those are easy, guaranteed points.
Stepping it up to the 2-mark questions. Exams love testing if you know why the exceptions exist. So why couldn't Mendeleev place hydrogen, and why exactly are noble gases so lazy and chemically inert?
It all comes down to electron configurations, right? Hydrogen is basically a split personality. It acts like a reactive alkali metal, but also like a halogen. Mendeleev just couldn't pin it down. And noble gases? They are inert because their outermost shells are completely full. They're totally satisfied. They don't want to gain, lose, or share electrons with anyone, so they just don't react. Okay, this is the big one, the 5-mark mastery question. This is what separates a good score from a perfect score. When you're asked to explain these trends, you can't just say what happens. You have to explain the actual mechanics of why it happens.
So let's structure this perfectly. Start with atomic size. It decreases across a period. Why? Because the positive nuclear charge increases, pulling the electrons in tighter. But down a group, size increases because you are physically adding entirely new electron shells. Now for metallic character, which just means how easily it loses electrons. It decreases across a period because that nuclear pull is getting stronger. But it increases down a group because as the atoms get bigger and add shells, those outer electrons are so far away from the nucleus that they're super easy to lose. Boom, full marks. And just like that, you have officially mastered the history, the rules, and the trends of the periodic classification of elements. You are totally ready to crush your exams. But hey, remember, this table isn't just a dusty poster on a classroom wall. It's a live, active map for discovery. Scientists used it to find things they didn't know existed. So, as we keep pushing the limits of science, what kind of wild, mind-bending elements do you think we'll discover next? Keep wondering, keep studying hard, and I'll see you in the next explainer.